All right, let's move forward. Let's look at the last part of this lecture set on x86, which is encoding the x86 ISA, right? How do we encode it in bits? So since our we are looking at we are looking at 32-bit ISA. So my main discussion would be on 32 bits, but definitely this part will also keep it more generic. So we'll also talk about how to encode instructions in other sizes, right? So let us first take a look at the general overview of every x86 instruction because x86 has been around for a long time. So there a lot has been done to ensure compatibility in the sense that today's code runs on yesterday's processors and yesterday's code runs on today's processors. Does not happen 100% of the time. For example, if today I take a code with MMX registers, and it will definitely not run on an older processor. But at least what we want is that all the code which runs on, let's say, processors 10 years ago will still run on today's processors, right? So that compatibility needs to be there. Otherwise, it's sort of a bad business decision otherwise. So let's take a look at the overview of instruction encoding. So since this is a CISC instruction set, instructions can have different lengths. Sorry, this should be CISC. CISC. Instructions can have different lengths, and the lengths can really vary, right? So the lengths can be different. Different instructions can have very different lengths and sizes. So this will make processor design difficult, but we'll decide this. We'll talk about this later. Let's take a look at the broad overview of the instruction encoding scheme. So the first 1 to 4 bytes, which are optional, have a prefix. So what is the prefix? The 1 to 4 byte prefix specifies, uh, this prefix field specifies the prefix. So for example, we have taken a look at the rep prefix in instructions, right? That we can have an instruction in the form rep move st. So this will essentially execute move st several times, similar to a loop. So there are many other prefixes. So the prefixes are typically also used to encode the data size. For example, the data size of the ISA. For example, in a 64-bit instruction set, we can use the prefixes to indicate normal registers and 64-bit registers and so on. So the prefixes, and also in a lot of extensions of the ISA, the prefixes come very handy. So that's the reason they can be anywhere between 1 to 4 bytes, so they can encode a fair amount of information. Another commonly used prefix is a lock prefix, which is used to specify that an instruction will execute atomically in a multiprocessor system. So we'll discuss more about this when we go to chapter 11. What I mean by atomically is that it executes as if it's executing in an instant, right? So nobody can see any intermediate state of the instruction's execution. So we will discuss in chapter 11, it's far more complicated than that. But the important point of the prefix field that should not be lost is that a lot of optional, well, I wouldn't call it optional information. The field is optional, but the information is definitely not. A lot of information which sort of specifies the behavior of an instruction, that is part of the prefix field, like whether instruction needs to be repeated or whether an instruction needs to execute in a particular manner. All of these fields are incorporated over here. The next is the opcode. The opcode can be anywhere between 1 to 3 bytes. Then we have 4 optional fields. One is the mod R by M bit, which specifies uh, what are the registers that are used in the instruction, and does the instruction use a memory operand or not, right? And since the CISC instruction set supports fairly complex memory operands with a possible scale, index, and byte, we have a special SIB byte, SIB scale index byte to encode this information. Subsequently, to encode the offset, which is also called the displacement, in x86, we have 1 to 4 bytes. mainly because in this case we are considering 32 bits. In a 64-bit ISA, the displacement can even be larger. This can be 1 to 4 bytes, and then additionally we can also encode an immediate in an instruction like an add instruction or something. So displacement and immediate are separate fields. So if we take a look at this, the smallest size of an instruction can be 1 byte because it will just have a 1 byte opcode. The largest size theoretically can be 4 plus 3 7, 8, 9 plus 4 13 plus 4 17, right? So from anywhere to 1 to 17 bytes, we can have an instruction. So this basically says in this sort of should convince the listener that the span of instructions in x86 is very, very large. We can have a lot of instructions between 1 byte and 17 bytes, and instructions can really, really, have very, very different kinds of encodings. So let's take a, so the opcode is specific to each and every, type of add and sub and multiply and divide will have different opcodes. So we'll also see the opcode encodes some other information, but we'll discuss that when we discuss the mod R by M byte. So the important thing is let's discuss the mod R by M byte. R stands for register and M for memory. So this is a single byte, and a single byte is divided into three fields, right? So a single 8-bit field is divided into three fields. So the first two fields are called the mod bits or the mode bits. So the mode bits over here determine the addressing modes of the rest of the operands, right? What is the addressing mode of the instruction? So let us call the first ones as source 1 and other as source 2. So if the mode bits are 0, 0, it means that the register indirect addressing mode is being used without a displacement, right? So basically, let me see. Displacement is same as the offset, so no displacement. The displacement is not being used, and 0, 0 indicates that the register indirect addressing mode is being used. So basically this would be an instruction of the form, let's say add EAX. So in this case there is no displacement, a register indirect addressing mode is being used. So pretty much the first source would encode EBX and the second source would encode EAX. So recall that we can have two kinds of instructions. We can also have this, right? So both of them will actually have the same mod R by M byte, but there will be one additional field in the opcode. So if you consider the opcode will have one additional field called the D field or the direction field. And the direction field is essentially a single bit, which can either be 0 or 1. And this indicates whether, depending upon the direction field, we will distinguish between these two scenarios. So whether the transfer is this way or the transfer is that way, this is indicated by the direction field. Alright, so now let's consider other modes. So if the mode is 0, 1, it indicates an indirect addressing which has a displacement, same register indirect addressing, pretty much in a base offset kind of mode with a 1 byte displacement. 1, 0 indicates that it's the same thing, it's, memory is being accessed. So in R by M, it's essentially the memory that is being accessed, but the displacement is 4 bytes. And if the mode bits are 1, 1, it means that the register direct addressing mode is being used. In a sense, the instruction is of this type, right? So there is absolutely no memory, and the operand S1 is actually a register, right? So no memory is being used. That is what the mode 1.1 says. It's only an operation on registers. And the first three indicate that one of the source operands is a memory. So now you probably understand very well that why only one of the source operands, one of the two operands that are specified can be a memory address, Mainly because we otherwise will run short of bits. So typically the base register will be saved in this field S1 and the other register will be saved in S2 and the direction of transfer will be specified by the D bit in the opcode. So what are the three modes for? The three modes are basically to specify the size of the displacement. 00 says that there is no displacement. 01 means that there is a 1 byte displacement. 10 means there is a 4 byte displacement. And 11 means it's not, memory is not involved, both the operands are registers. If we have an instruction, let's say of the form inc ECX, right? So in this case, there is no memory, but the value of ECX is saved in source 1, right? Or if we have another thing of, let's say, not EDX. So here also EDX is stored in source 1. So source 1 is considered as the primary source, especially if there is only one operand. If there are two operands, then at most one of them can be memory, and the memory operand needs to encoded via source 1, and S2 needs to be a register, has to be a register, right? So that's the general idea. Now let's discuss the mod R by M byte in some more detail. So as I mentioned in the previous slide, the reg field specifies the register operand if necessary. The mod bit in consonance with the R by M bits determines the format of, so both of them, both the bits determine the format of the memory operand if it exists. So let us now discuss some special cases. So if R by M is equal to 100, which is essentially the encoding for the stack pointer, this tells the hardware that look, let us use the scale index byte, scale index base, the scale index and based on the SIB byte to encode the instruction, to look for the encoding of the instruction, right? So let me repeat. If the R by M bits over here, so if the R by M bits contain 100, so 100 corresponds to the encoding of the stack pointer. This tells the hardware that an SIB byte follows, so let us ignore this part and look at the contents of the SIB byte. And the SIB byte should encode a memory address of the form, with a scale, an index, and a base. So something like EAX plus 2 times EBX. Alright. Okay. So let's take a look at the SIB byte, the scale, index, and base. So in this case, this is an 8-bit field. So there are 2 bits for the scale. So there are 4 values of the scale: 00, 01, 10, and 11. 00 specifies a scale of 1, right? So basically this would be at the form EAX plus EBX. 01 has a scale of 2, so this would encode address of the form EAX plus 2 times EBX. Similarly, 11 encodes a scale of 8, so this would encode a address of the form EAX plus 8 times EBX. So both the index and the base are 3 bits each, so they follow the register encoding scheme. So we have 8 registers, right? So we have 8 registers in our uh, repertoire. So the register encoding scheme encodes these 8 registers, and so this will be there on the next slide. So basically for 8 registers, how many bits we require? We require pretty much 3 bits. So there are some important rules that need to be kept in mind. The first is that ESP cannot be an index. All right. So basically the ESP field cannot be an index over here as an invalid index. So this also makes sense. Why would anybody make the stack pointer an index? You might want to make it a base register, but making it an index is not right. The other is that the offset in the memory address needs to be specified in the displacement field. All right. So that is the second point that needs to be kept in mind. Let us now take a look at the register encoding. So as was promised in the previous slide. So the code of 000 is the register. We start with EAX. Then we have ECX and EDX with codes of 001 and 2. Then we have EBX with a code of 011. ESP is the stack pointer 100. EBP is the base pointer 101. Then we have ESI and EDI with codes of 110 and 111 respectively. Right, so these are the 8 registers. Now I want to make 2 points regarding 2 special cases. So the first special case, as we have discussed, is that if the R by M bits are 100, which in this case actually point to the stack pointer, then what we do is that we essentially discard that information. Well, discard it in the sense we don't use it in the addressing, and we use the SIB byte instead. So let's go back to the slide. So in this case, if the R by M bits are 100, this basically means, so this register remains as is, we'll not touch this, but this tells the processor that an additional SIB byte follows and read the scale, index and base registers from the SIB byte, and depending upon the mod there can be a displacement as well. Let us discuss the second special case. The second special case is when mod is equal to, the mode is equal to 00 and R by M is equal to 101. 101 in this case is equal to EBP. Right, so we have not discussed this, but let me discuss it now. So let's go back to that field. So in this case, let us assume that the mode is 00, means it's register direct, and let me just delete this, and the R by M bits are 101, right? So 101, as we see from this, points to EBP. So the mode is 00 and R by M is 101. So in this case, what should we do? What we should do is use register indirect, but we'll not do that. So we'll treat the mode bits being 00 and R by M being 101 as a special case. And this special case corresponds to, so now that you have seen this, let me again go back. I'm sorry. So this special case corresponds to memory direct addressing. So in this case, we don't use any registers in the addressing. Instead, the 32-bit displacement is inferred as a memory address. So we directly use that as the memory address. For example, nothing stops us from writing. We can always write an instruction of this form. Right, so this is a valid memory address. So basically it's a valid hex, 32-bit address. And so we can always write an instruction of this form. And so in this case, we are specifying the address directly without any registers. So this is called a memory direct addressing mode, and this can be achieved by the means of the special case, where the mode bits are 00 and R by M is equal to 101. So that is where we can achieve this, right, as a special case. So now the question that most students ask at this point is that how would we then, write an instruction, encode an instruction of this form EAX and EBP? Well, so in this case, what we would do is that we will actually use the first option and we will set the R by M bits to 100 and the scale index base. So in the scale index base, we will essentially have EBP as the base and we'll have ESP as the index. So in this case, since ESP is an invalid index, the hardware will ignore it. So as a result, what will only remain is the base. Right, so this is something that can be done. And so as I said, sometimes in x86 instructions, some such special cases need to be, needs to be done to basically ensure that we are able to encode everything that we want to, right? And some cases such that disallowing the stack pointer to be an index is fair because there'll hardly ever be any reason to actually have the index as the stack pointer. There's also one more correction I'd like to make. I had said that in a 64-bit instruction set, the displacements and the immediates can be larger. That's not correct. The displacement in a 64-bit instruction set, if you take a look at the latest Intel manual, the x86 64 instruction set, the displacements and the immediates are still limited to 4 bytes only, right? This is the correction that I want to make. And the hardware extends the sign from 4 bytes to 8 bytes. That's all. Now let's consider an example. So let us encode the instruction add EBX, EDX plus 2 times ECX plus 32. So let us assume that the opcode for the add instruction is 0x03. So now that we know the opcode, let us calculate the value of the mod R by M byte. So in this case, our displacement fits within 8 bits. Hence, we can set the mod bits equal to 0, 1, corresponding to an 8-bit displacement. Alright. So the first two bits are 0 and 1. Then we understand that we need to use the SIB byte because we have a scale as well as an index. Thus, we set the R by M bits to 100 at the end. The destination register is EBX, its code is 011. So the destination register comes at the middle, so this is EBX. These are the mod bits 01 corresponding to an 8-bit displacement. And 100 indicates that look, go and take a look at the SIB byte. So the encoding of the mod R by M byte is 01, 011, 100, which can be seen as 0101 as 5 and C is 1100. Now let us calculate the value of the SIB byte. So in this case, the scale is equal to 2. So we encode this as 01 and encoding comes over here as the scale. The index is ECX, which is 001. So this is the next field. And the base is EDX, which is 010. That is the next field. Hence the SIB byte is 0100110, which is 4A, 0x4A. The last byte is a displacement, which is equal to 32 or 0x20. Thus the encoding of the instruction will be 03 for the opcode byte, right? So this is the opcode. 5C, this is the mod R by M, mod RM byte. 4A is the SIB byte, scale index base byte. 20 is the displacement. Alright. So this is the encoding, this is the 4-byte encoding of the instruction in hexadecimal. Okay, this was a long chapter, so we have come to the end of the x86 chapter. So now we have a fair understanding of the different variants of x86 instruction set, 16 bits, 32 bits, 64 bits. So the x86 instruction set is very large and it has a lot of extra features. So one large set of features that we have not covered in this lecture is basically the other extensions of the instruction set, particularly what are called the vector instruction sets, which we'll discuss in chapter 11. So that contains mainly the MMX and the SSE instruction sets. So we will need to discuss that at a later point. But in any case, the coverage of MMX and SSE is very limited in this book. So readers need to take a look at sources on the web or Intel manuals to get a better understanding of these two ISAs. But other than that, the basic kernel of the x86 ISA has been covered in this chapter. Alright, so now I will see you in chapter 6 where we discuss the fundamentals of digital electronics.